Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
The second talk is entitled COEVOLVE, a joint point process model for information diffusion and network coevolution. We have Lei Song here from the Georgia Institute of Technologies, and he'll tell us a bit more about this one.
Thanks for everyone for attending. The first offer, the student of mine cannot make it due to visa issue, and the last offer I'm going to give the talk is that this is a joint work with a bunch of other students from Georgia Tech and also my collaborator Manu from Max Planck Institute. So essentially this work is about the information diffusion and network coevolution. When we look at online social network, essentially it's an information network. People go online for some purpose. Either they go to Twitter to find useful information, or they try to connect with friends to share some joys of life, or they go to Quora or something else to find or acquire knowledge, or in LinkedIn you try to find job opportunities. So essentially, there's two processes going on in this social network. One is information diffusion process. Another is the evolution of the network due to this information diffusion process. So I'm going to use these running examples in my talk. Essentially, you have a small number of users in this social network: David, Sophie, Christina, Bob, and Jacob. They are linked to each other in such a way, and there may be some other users, but we'll ignore them for the moment. For instance, David may tweet about some information at 1 p.m., right, saying that this is a cool paper, and then Sophie respond to it and agree with David's tweets, okay? And then this information might propagate further down to the followers of Sophie. For instance, Christine may also tweet about it. In this information propagation process, the source of the information, which is David, is explicitly acknowledged in all these tweets and retweets, okay? And Jacob now sees the information and retweet again. At the beginning, Jacob is skeptical about the information. But afterwards, Bob also tweeted about his paper and agreed that this is a good paper. And then also in Bob's tweets, it's going to acknowledge the source of the information, which is David. So now Jacob has two neighbors, which is tweeting about a particular paper, and the particular source of information from David, and then Jacob go and check again, and really this is a good paper. Now Jacob feels that this information source, which is David, is very useful. So he decided to create a link directly to David, okay, at 1:45. So essentially the information diffusion process is going to drive the creation of this link in this social network. In turn, the creation of this new link is going to sort of change the way information diffuses across the social network. For instance, the next time when David tweeted about a car, okay, and then Jacob is going to see immediately and then will respond very fast, okay, in 3 minutes. David is going to respond and agree that this is a really good car, okay? So essentially, there are two processes going on here. More specifically, there's a diffusion network behind it. And then there's an information propagation process or information diffusion process in this hypothetical information network. And then diffusion network structure is going to support the spread of information. And then the information diffusion process and the spreading of information is going to drive the creation of the link in this social network. In turn, when a new link are created, the information diffusion network is going to change and alters the way that the information propagates in this process. Essentially, we want to model these two processes which are interacting with each other, and we want to feed it from the data. Previously, there has been lots of work on just looking at the network structure or the evolution of network structure itself. There also has been lots of modeling the information diffusion by itself. Recently, people are able to sort of collect the information or data which is both about information diffusion, link creation, and able to do some kind of empirical study about the interaction between these two processes. And people find empirically, indeed, the information diffusion process is going to drive the creation of links. So, but if you look at the model, probabilistic model for these two interacting processes, it's still missing in the literature. So essentially, the goal of the paper is to provide such a joint probabilistic model for both information diffusion and network evolution. And then we also want to sort of figure out how do we actually simulate events from such a probabilistic model efficiently. how to estimate parameter from such a model, and whether the model is going to generate realistic-looking information diffusion traces, and whether it's going to create the evolution pattern of the network, which is realistic as well, and whether the model can make very accurate prediction. Okay, this is the goal of the paper. So I'm going to start with the sort of the modeling part. How do we actually formulate this problem into a probabilistic model? So the way we approach this problem is to sort of distinguish two types of events in this social network. The first type of event is going to associate with the tweets and retweets. So we are going to essentially represent each one of these tweet or retweet as a triplets, containing both the destination and the information source and the time when these retweets or tweets are going to be created. For instance, when David generated his original tweets, the event is going to be recorded as DD at 1 p.m., right? And because the source, it is original tweets, the source and destination are the same. And when Jacob retweets a tweet originated from David, we're going to record it as JD 135. So we're ignoring the path where this information is propagating. We just take the destination and the source of this information and record it down, and also the corresponding time point. The second type of event in this information diffusion network, when you try to model the coevolution network structure, is going to be these link creation events. Again, it's going to be some kind of triplets containing both the destination, source, and the time when the link is going to be created. For instance, for this particular link between Jacob and David, you can record it as JD145. Of course, each one is node in social network is not going to just generate a single event. It's going to generate a sequence of events. For instance, Bob is going to generate original tweets at 4 p.m., and then Jacob is going to retweet it. And you're going to record his retweets as JB410, right? And then Jacob can also generate its original tweets. You record it as JJ5, yeah? So essentially, we can organize all these events or tweets or retweets generated from David according to the source of this information. So we are going to organize all these events generated in Jacob as several timelines. Each timeline is going to correspond to one of these sources, and we're going to record explicitly the time when these particular retweets are generated. So you can do the same thing for all other nodes in the social network. For instance, Christine, Bob, and Sophie, David, they all have their own sequence of timelines. Similarly, for Jacob, you also have a sequence of link creation events. At the beginning, he creates the link with Christine and Bob. Later on, he creates the link between to David, and then you can create another link to Sophie at some other point in time. So you can also record this sequence of linking events for this particular user J as several timelines. Each one corresponds to one source where the link is coming from, okay? For instance, in this particular case, we only consider the creation of link once, and that's why the corresponding timeline only has one event. So mathematically, if you want to model these sequence of timeline, this sequence of event or point processes, typically use the so-called counting process to describe it. Essentially, you take each one of these timeline, and then you just count the number of times that you have particular events up to time t, right? So for Jacob, you have a sequence of retweeting events. You have a sequence of counting process associated with it. So we call these retweeting process identity reviewing, in the sense that each one of these timeline is going to correspond to one source. So it's keeping the identity of the source. Similarly, we can also model the link creation as some counting process A. But in this particular counting process for the link, the value is just 0 and 1. It's driven by the information diffusion process. To describe this counting process or parameterize them, commonly used quantity is going to be this conditional intensity function, which is going to be the conditional density over the conditional survival function, okay? This H. So the meaning of this conditional intensity function is going to be the probability of event occurring in small time interval between t and t plus delta t, but given that it hasn't occurred before time t. So once you have this conditional intensity function, then you can parameterize your counting process as an integral form plus some kind of zero mean martingale. okay? Depending on how you actually parameterize these conditional intensity function, then you will have very different type of point processes, very different behavior. For instance, some familiar conditional intensity function is going to be is going to be constant. It doesn't depend on time. It doesn't depend on the history. This is going to correspond to a vanilla Poisson process, where you tend to see event happening in time in a more uniform fashion. The occurrence of event is independent of each other. Okay. You can also take into account history and design your conditional intensity function to take into account history. For instance, for each event happening in the past, you can add to the intensity of something happening in the future. You can add the function, which is exp, the difference of your current time and historical time ti. And if you have lots of event happening in the recent past, it's going to be a high intensity. Very often you also write it as some kind of convolution between the kernel function, exp minus t, with this counting process. Okay? It's very good for modeling self-excitation behavior. We're going to see how it's going to be used in the later diffusion process modeling. So another one I'm going to introduce is something called survival process. Essentially, in this particular process, you only allow event to occur once. Once it occurred, the counting process is going to be 1, and then you look at the difference between this counting process of 1. If it's 1, you zero it out. Okay? You do not allow any further event to be generated. We are going to use this Poisson process for the diffusion process and also the link creation process. The Hawkes process is going to be used in this information diffusion process, and the survival process is going to be used for modeling the link creation. If I put these specific examples of point process into this big picture of interacting process between information diffusion and network creation, it's going to be something like this. The diffusion network is going to be many counting processes for each pair of node, but the value is between 0 and 1 is time varying. And the information diffusion is going to be also recording this count process, MT. It's going to be modeled by Hawkes process and then Poisson process. And the link creation is going to be driven by this information diffusion. It's also going to be modeled by Poisson process and the survival process. And more specifically, I'm going to explain this information diffusion process using an example, and also the link creation process example. You can see the general formula in the paper. So essentially, for this information diffusion process, we want to model 2 phenomena. The first phenomenon is going to be original tweets. People just generate original tweets using the Poisson process out of their own initiative. For instance, David can tweet about his own ideas, right? So you have this counting process, NDD, for original tweets. It's described by this gamma DD, and it's going to be constant due to some just own initiative. So when Jacob trying to retrieve the original tweets from David, he's going to look at the number of tweets from his 2 neighbors, which is Christine and Bob. If Christine and Bob, they have retweeted the David very often, and then Jacob is going to expose to many of these tweets originated from David, then the intensity of Jacob retweeting David is going to be high. Okay, we try to capture these, the higher exposure, the higher the intensity of retweeting someone in this count process. Essentially, we are going to use Hawkes process. Essentially, we are going to first look at the counting process from Christine. How essentially you just model the exposure due to Christine, and this time is going to be the exposure due to Bob, right? You suddenly together aggregate information for all these neighbors, which is going to retrieve the David, and then pass it through a Hawkes process to model this long-term memory. So this is our information diffusion process. You have such a process for each one is node, and for each one is information sources, okay? Similarly, you can use point process to describe the link creation process, okay? So essentially, we try to capture this intuition that if Jacob is retweeting very often the tweets originating from David, and if he hasn't created a direct link to David, it's more likely that the Jacob is going to do that in near future. So essentially, the intensity function describing this counting process AJD is going to look like this. So first, you are going to check whether the link has been created or not. If not, you're going to have some intensity. And then you're going to look at how many times Jacob has retweeted some tweet originated from David, okay? If you do that a lot, and that means that the David is really useful, very good information sources. It has a higher likelihood of being linked, okay? And then, of course, in the end, with respect to where the information is coming from, Jacob may have some exploration, right? He might just randomly create some link to other people, right? So essentially, we are going to just use these Hawkes process and also the survival process to describe these two interacting prime processes. And as you can see that in this link creation process, you have these network change varying over time. And also for the information diffusion process, there's also these network, which is changing over time. That's how the two components tie together and interacting with each other, okay? So in the paper, we have designed the efficient way actually to simulate event from this joint probabilistic model. And here, I'm not going to explain the detail, but instead, I'm just going to show you a simulation of the sort of the retreating events sampled from the process, and then also the link creation events sampled from the process. So the coloring of this node is going to correspond to the intensity process. So we didn't sort of visualize the source identity because it's hard to visualize. And you can see that the tweeting events and the link creation event essentially interleave with each other. In the end, you obtain some network. So we have some algorithm which allow us to scale out to millions of nodes. You can check the paper for detail. And another nice thing about the model is you can actually estimate the parameter of the model from real data. Suppose you have crawled your Twitter data set, and then within the time window between 0 and t, it contains n node, and then it has a bunch of retreating events, also a bunch of link creation events. You can actually estimate the parameter using maximum likelihood. You will have one term for each one of these retreating events. You will also have one term for each one of these link creation events, and then you're going to have some normalization term with respect to a pair of nodes. So the nice thing is, using the model I explained in earlier slides, the intensity function gamma and lambda is going to be linear in the parameters. And that translates to the overall objective function is actually concave in the model parameters. And you can actually find a global optimal of your parameter estimation. And then another thing, if you dip into it further, is the estimation procedure actually decomposes, decouples according to these model parameter, okay? And you can parallelize it. So as you increase the number of sample size, you can find that you can estimate parameter in increasing well, okay? So the next question is whether the generated network, a simulated network, can generate realistic property as we see in real-world networks. So indeed, we can do that. We can actually control these parameters, alpha and beta, alpha corresponding to the link creation parameter due to information diffusion, beta corresponding to this excitation, retreat excitation parameter. And as you increase this parameter, you will generate a network which range from random graph to a graph which has a degree distribution, which has a power law distribution, which you see in the real-world network. So if you compare this network, these are the diversity of the type of network you can generate from such a model. You can also look at the diameter of the network. As it evolves over time, diameter essentially shrinks over time, okay? Also observed in real-world network. So you can produce a bunch of other statistical real network, not just related to network structure. It will also related to the Cascade, information diffusion process. As you increase these information diffusion-driven link creation process, you will see that you will see more often these fat and short cascades, which is also observed in real-world network. Finally, I have 3 slides just briefly explaining these real experiment for predicting the information diffusion process. We take a Twitter data set which contains millions of users and millions of link creation and retweeting events, and then feed a model using this convex optimization. And once we feed a model using the 85% of data, and we're going to predict 15% of data comes in future. So we find that by jointly model the coevolution information diffusion process, and you can actually predict the creation of link more accurately than alternative models. Similarly, if you try to predict the next retreating events, using this coevolution model, you can also predict much more accurately than alternatives. So with this, I'd like to conclude. Essentially, what I have presented to you is a joint point process model for information diffusion on the one hand and also the network coevolution. It has a very simple generative model, and you have efficient simulation and estimation procedure. It can reproduce a very good, realistic looking microscopic property and making very good predictions. So essentially, there are many possible extensions you can do. For instance, we haven't looked into the breadth and depth of the nodes. You can also model the link deletion process. You can also incorporate many of these node attribute information and tweet contents to make this model more realistic, more predictive. I welcome you to have any suggestion about this model. Thank you. Yeah.
Could all the spotlight speakers maybe just line up on the side, or on this side actually. So are there any questions? We have time for 1 or 2 questions.
Thanks very much, neat talk. Hey, so you have a triple, and you say the originator of the tweet and the final recipient of the tweet, and then the time of the tweet are the 3 things. And my sense is if David tweeted me and I tweeted someone else, no one would link to David. But if David tweets Oprah and Oprah tweets someone else, everyone links to David. So I'm wondering, what is the role of the intermediate people and their kind of importance in creation of links? And what is the effect of leaving that out of the model, or is it implicitly included in the model?
Yeah, it's implicitly included in the model. So actually, every node is going to have this information diffusion process, counting process. And when you try to generate some kind of retweeting events, you're actually aggregating counts from all your followees. And if they tweet a lot or very often, then it's actually going to boost your tweeting probability. So it's implicitly included. Yeah.
Okay, if there aren't any other questions, let's thank both Lei and Maren. Thank you.
Sorry, I have a question.
Where
Sorry.
are you? Okay.
Here.
Speak.
Yes. Over there.
Oh,
Yes.
Oh, yeah.
So as time goes to infinity, you will get the complete graph, right? So
That's right.
So it's a bit frustrating. I mean, it would be nice if there was a more interesting stationary distribution. So maybe, I mean, you allude to it at the end with the link deletion. So maybe, did you think about that? Like a
Yeah,
way
exactly. That's the extension I'm talking about. You can either allowing for node birth process and death process. So you will have growing number of nodes, then you won't get a complete graph. Either you can have link deletion process. That will also prevent you from having a complete graph. So it's very easy to incorporate. And you still get context optimization for estimation of parameters. You still get this efficient simulation algorithm. We have some preliminary work on simulating this type of process, but it's not in the original NIPS paper.
But you don't know what is a stationary distribution? I mean, can you
No,
say something about it?
we don't know about a stationary. We don't have a closed-form formula for that. Yeah, it would be nice to have it. Yeah.
Okay, thanks.
Okay, let's thank the speakers again.
Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.